In this part of the lecture, we will look at the format for instructions that are used to make decision. A typical C code where you need to make a decision is where you are doing an equality test, like in this example, and then you do different operations depending on the value or the result of the test, the equality test. So if I look at this code for in RISC-V, and let's assume that those are the registers where each one of the variables in the C program are stored. The RISC assembly for this code will be something like this. I will have a branch not equal test. And the first thing to notice is that in the original C code, the test was an equality test. We are testing whether I was equal j, while in the assembly code, we are testing whether I is not equal j. The reason that we do that is that in assembly code, we are asking under which condition we need to jump to the place where we're going to compute the else of the code. So if S3 is not equal S4, which means that I is not equal J, then I will be computing the addition. But then immediately after I compute the addition, I need to jump out to the merging point or to the join point that occurs after the if. So I need to go to the exit. The way I go to the exit is by doing an unconditional jump. We're going to see in the third part of this lecture how the unconditional jump is encoded and why we are using a jump and link instruction for the unconditional jump. So for right now, you can just read this instruction as a go to. It goes to the exit. And then after I have that unconditional jump, then I'm going to have the code for the subtract. So if the condition was such that I was not equal to j, the branch not equal instruction will be jumping straight into this code where I'm going to be doing the subtraction. And right below the subtraction, I have the join point where whether I did the addition or the subtraction are going to be executing the next instruction in the program. So this is a simple code example. And we will now move this code example in here in this slide. And the only thing that I have changed from the previous slide is that I have added the memory addresses in front of the instructions. I'm assuming that this code is stored at those memory addresses. And we're going to see in a minute why we needed the memory addresses to encode these instructions, to understand the branch not equal workings. So the branch not equal, what it's going to do is test the value of the register RS1 and the register RS2, in this case is S3 and S4. And if they are not equal, then we're going to take the program counter and we'll add to the program counter the value of the immediate. And that 1B0 means that there is an implicit 0 bit. The bit 0 is always equal 0. If the condition is not true, which in this case it would be when S3 and S4 are equal, then I will simply increment the program counter by 4. So here's the format. The branch instruction uses an SB type format. Here's the format for the branch instruction. And in this, we want to jump for this branch to a label that's 12 bytes away. If we look at the addresses here, the branch is at the address 1000,000, and the target of the branch is at the address 1000,000C. So this value that we want to add to the program counter when the condition is true should be 12. I'm skipping 3 instructions. Each instruction occupies 4 bytes. 3 times 4 is 12. So that will be the immediate value that we're going to be using the branch instruction. So if we simplify the code a bit so that we can see a little better. So if we map now, first of all, we need to find out what is the value 12 expressed in 13-bit signed binary. So 12 expressed in 13 bits binary will be a number of zeros followed by 1, 1, and 0, 0. If you recall, the position of the numbers are 1, 2, 4, 8. So 8 plus 4 is equal to 12. So we're going to take this value and will sign extend to 32 bits, and that will give me the value that I need to add to the program counter in order to go to the target of the branch. So if I add the current value of the branch not equal, that is the address, sorry, of the branch not equal instruction, it is at the address 1000,000. I add that displacement. I obtain the new value of the program counter, that is the 1000,000C. Now, if I break down the number 12 representation in 13 bits into these bit fields where I keep the bit 0 separate, and then I have the bits 1 to 4, followed by the bits 5 to 10, and then the bit 11, and then the bit 12. Now that I have broken down those 13 bits into these fields, one of the things to note is that the bit 0 is always 0 and does not need a representation. The reason that the bit 0 is always 0 is because I can only branch to even addresses. I can never branch to an odd address, so there is no reason to represent the bit 0. It always will be 0, so it will not gonna appear in the instruction representation. We'll take the bits 4 to 1 and we'll put in that position of the instruction. Then we're gonna take the bits 5 to 10 and we'll put in that position in the instruction. Then we'll take bit 11 and move to the right of the 4 to 1 bits. And then we're going to take the bit 12 and we'll move to the most significant bit of the instruction. That is how we're going to compose the fields for the immediate value of the branch instruction. So now that we have the field composed, and now we have expressed the 4 to 1 here as a hexadecimal number, so it's 0x6. We have expressed the 10 to 5 also as a hexadecimal number. Not all bits are used because this will be 8 bits and we only have 6 bits represented. Next, we need to encode the value of the registers. S3 is the register 19 and S4 is the register 20. So we have to have the numbers 19 and 20 in those fields. The function 3 for the branch not equal is 0x1, so that specifies the variant for the branch not equal specification, and the opcode for the branch instruction is 0x63. So if you convert that into binary, we obtain this value in binary for the branch not equal S3, S4, and jumping 12 addresses forward, and in memory we're going to see 0x01499663. So one thing to note is that although in the assembly code we see this label subtract and we see the subtract here, in the binary representation of the code those labels never appear. What gets encoded into the binary representation is the distance in memory addresses between the position of the branch not equal instruction and the position of the target of the branch, that is the sub instruction that has the subtract label in front of it. So if we recap what we just learned, we learned that the branch instruction actually has a label, subtract, that appears in the assembly program, but never appears in the binary representation of the program. We have also learned in this part of the lecture that the format for the branch instruction is such that the immediate field has the distance between the branch and the target. We also have learned that there is this ghost 0. The bit 0 of the immediate field never appears in the instruction. It is always implicit equals 0. The immediate value is sign extended to 32 bits. Therefore, it could be negative. And if I have a negative immediate value, it means that this is a backward branch, a branch that is branching to a memory, to an address that appears in the program before the branch. And backward branches are very useful to create loops in the program. because when you have a loop, you have to go back to a place that you have been before, so you do a backward transfer of control in your program. The next part of this lecture, we're going to learn about the jump and link instruction.